Okay. So this is a molecular effect. This is a process effect. In addition, if you begin to dissolve the polymer in a solvent, right? Solvent is low molecular weight, low viscosity. Polymer is a higher molecular weight. So you will get some intermediate molecular weight. And you'll get an intermediate viscosity, right? Of course, the more polymer you put, in this case, if you see, this is just molecular weight going up. 340, 300, 440, 30,000. Okay. So on the one hand, if you raise the molecular weight of the polymer in a same solvent, you increase the viscosity. The more polymer you put, so if you increase the concentration for any given molecular weight, you will increase the viscosity. So what does that mean? What that means is sometimes when you use a polymer solution to disperse particles and then create a coating or create a shade, right, by slip casting or so on, you want to control the rheology, you can do it in two ways. You can adjust the molecular weight, or you can adjust the amount of polymer. Okay, and in both cases you can adjust the rheology of the fluid in that manner. Of course, different chemistries have different interactions with solvents, different polymer chemistries. And so by changing that, you're going to change the viscosity as well. Right? So shear or pressure is one process parameter. What is another variable that we can change in the process that affects the way we can create shapes? Okay, great. So temperature. So then the question becomes, what happens to viscosities? Okay, in this case, it's a function of molecular weight, right? You go to a higher molecular weight, you get higher viscosities, right? So then the question is, what happens when you change the temperature? Right? What do you expect to happen when you change temperature to viscosity? Yes, depends, right? Right. So if you increase the thermal energy, diffusion properties are going to increase of any system, right? And so you're going to reduce viscosity. Of course, if you have chemical reactions occurring because of the increase in temperature as with thermosetting, your viscosity is going to increase. Right? In this case, again, another common, we saw in the previous case all hydrocarbons, right? Like polyethylene and its variants. Now you can have some polar material as well. So PEG is polyethylene glycol, and that can dissolve in water. It's polar. PMMA, we looked at that, plexiglass, right? Polymethyl methacrylate. Again, the same type of principle. As you increase the amount of polymer, PMMA, which is a much higher molecular weight compared to PEG, right? What happens? At any given rate, goes up. Right? As for the same shear rate, as you keep increasing the amount of PMMA, viscosity is going up. Right? But overall, viscosity reduces as you are increasing the shear rate. Okay? So this is the structure of polyethylene glycol. This is CH2, this is CH2, and there's an oxygen over there. And there's hydroxy groups at both ends that allow for dissolving in a polymer. Right? We talked about block copolymer dispersants. So if one block is like this and another block is more, which is short, right, is hydrocarbon in nature, then it is possible that you might be able to absorb this on the surface of the powder, and then the other block can separate particles from each other. Polyvinyl alcohol, CH2CH, and you put a alcohol group, okay, that makes it hydrophilic. Right? So you cannot use that for your electrochemical experiments because it's going to dissolve in the acid. Right? However, for aqueous dispersions, you can now try to see how they can be useful. And so again, a combination of these, what happens is, in this case, as you begin to, what we have as a plot over here is that you can now use water to dissolve the polymer after molding, to dissolve PEG or to dissolve polyvinyl alcohol. The longer you wait at a given temperature, the more polymer comes out. Right? And so instead of using an organic solvent such as heptane, octane, right? You can now use water by changing, you change the chemistry of the material, how you remove the material, right? Whether you use aqueous processing or non-aqueous can be controlled, right? So flow properties, strength, removal properties by dissolving. The final thing is dissolving removal properties by thermal processes. Right? You heat up some material, in this case it's polyisobutylene, and you begin to break bonds. Right? You heat up anything, you provide sufficient energy to begin to separate the atoms from each other, overcome the bonding forces, and you end up forming free radicals. If many of them break up, you end up having low enough molecular weight gases that can escape from the pore structure. So some people made some simulations as a function of time and temperature as to what happens to this type of by calculating thermal energy and bond energy, you can begin to simulate at what point some chains begin to break into different fragments. Okay, so probability of a chain breaking at a certain temperature by overcoming bonding forces can be calculated, and basically at a given temperature, if you wait long enough, more bonds can be broken. Probability of bond failure is breaking is higher, and so you can end up making smaller and smaller fragments. And some people are, so you can at one level, from using physics or chemical principles, quantum chemistry, quantum physics principles, you can begin to actually design a polymer to break down at the temperature you want and try to balance it with the temperature at which the powder begins to react with the polymer and form carbides and other things, right? And so you can go to that level of sophistication if you wish, compared to just doing trial and error in terms of designing a polymer to break down at the temperature that you want by adjusting the chemistry. So to put everything together, in this class we looked at powders, at polymers. The previous class we looked at powders. So what we will do for the rest of the day is mainly look at how powders and polymers combine with each other. One of the major things is we looked at a lot of different shape and size diversity in powders yesterday, right? And a lot of different chemistry diversities going from ceramics. So this gives a relative consumption in the marketplace of different types of powders. And it is dominated in injection molding, for instance, by the steels. And the ceramics end up being a more minor component. Of course, it changes depending on process to process. In this case, it's most of the consumption based on for injection molding statistics. So mainly the thing is you have chemistry diversity, you have shape and size diversity. Now we have to see for the different types of polymer chemistries and those variables, how properties change. And one type of property that changes is viscosity as you increase the amount of powder. So on the y-axis, you have viscosity of the mixture relative to the viscosity of the polymer, the binder. B is binder, M is mixture. And so when you talk about relative viscosity, it is viscosity of the powder polymer mixture compared to the viscosity of the plain polymer. Right? When we looked at the viscosity of the polymer, if you increase the molecular weight, what happened to the viscosity? Okay, so it increased. So now what happens is now you're looking at the mixture for a given polymer viscosity, right? If you increase the amount of powder, phi is referred to as a volume fraction. Okay, I'll tell you what phi C is in a minute. But as you keep increasing the amount of powder, what happens to the viscosity of the mixture, right? So viscosity of the mixture increases. So even small molecular weight liquids that contain powders are going to have high viscosity after a certain point. Okay. Yesterday, when we were talking about packing characteristics, we said that there's going to be a limit to how much powder you can fill in a glass, right? And that is less than the theoretical density, right? So this phi C refers to the maximum packing fraction of the particles in a given volume. Okay. So phi is volume fraction, that is of the total volume that is occupied by the polymer and the powder, how much is occupied by the powder, right? So you have some powder and the space between the powders is filled with the liquid, right? And so the combination, the combined volume, that is fraction occupied by powder, fraction occupied by polymer, the combination of the two will be 1, right? Assuming there's no porosity. So phi, the term phi refers to volume fraction occupied by powder, and so 1 minus phi will be the volume occupied by the binder. So why do you have this increased viscosity or increased resistance to deformation as you increase more particles? So when you have a lot of polymer, you're dealing with this case. Low volume fraction of powder relative to the maximum packing fraction of powder. So the space between the polymer, the space between the powder surfaces is separated by the polymer completely. And so that acts as a lubricant, and the mixture can move more easily, which means you have lower viscosity. At the other extreme, when you have powders rubbing past each other, so the powder surfaces are all in contact with each other. There is some polymer, but there's not a whole lot, right? In that case, you're going to have a lot of friction between the powder surfaces, and so there's going to be more loss of energy that you apply for deformation. So the resistance to deformation is going to be the highest. It's going to behave like a solid. Right? So you have some intermediate case where there is a small layer of polymer separating the powder surfaces, and it is now closest to the maximum packing fraction of the powder. And so that is the critical stage where the viscosity ends up shooting towards infinity. Right? There's a transition point between behaving like a liquid and behaving completely like a solid. Right? Solid, infinite viscosity. Right? If you look at the curve going up like that. So this is the relationship between, now we are transitioning between just looking at the powder separately, looking at the polymer separately, to the point where now you're beginning to look at the mixture. And the first thing that changes is viscosity changes as a function of how much powder you put. More powder you put, the more viscous, the more difficult it's going to create a shape. As a result of this packing fraction term, now can you think about how the other properties of the powder that we talked about in the previous class affects flow? So if the packing fraction is lower, what happens to viscosity? Can you guess from that curve? So two different powders, two different packing attributes. One packs poorly, one packs nicely. What is going to happen to viscosity? as phi c reduces, what happens to viscosity as phi c becomes smaller? Right? This is a so the relationship is this is viscosity, right? And this is phi c, and this is -2. The closer you get to critical, the higher the viscosity, right? If the critical is lower, you're going to get to the infinite viscosity sooner, correct? And so poorer packing powders are going to have poorer flow characteristics. Got that? So the closer you get to critical, the greater is the resistance to deformation. So you get faster to critical solids loading at lower packing fractions. Right? Maximum packing fraction is going to get faster, so you're going to have poorer flow characteristics.
The shapes really odd to get the critical point earlier.
Yes, so good. So that brings to my question, what are the different ways in which you can affect packing density? And so shape is one. What else? We looked at another parameter. Pardon? Yes, very good. So if you have very fine particles, right, they're going to agglomerate more, and that's going to affect the packing density, right? And then third one, size is going to make, and that's going to affect the surface area. There are going to be more interactions. The higher the surface area, the more particle-particle surface interactions, higher the viscosity, right? And so that's going to affect viscosity as well. And then we talked about one way in which you take large particles and you fill the space with small particles. What happened? Right? And so, yes, so the particle size distribution is going to make a difference. So let's take an example of all of that, okay? So amount of powder in the mixture affects rheology, step one, right? You begin to change particle size. So this is viscosity as a function of volume fraction of the powder. And as particle size increases, what happens to viscosity? Right? Okay, particle size affects rheology. Step two, right? Viscosity as a function of volume fraction. You begin to change shape. What is happening as you go from which shape works best for reduced viscosity? So this one, spheres work. So you change the shape. So what does it tell you in terms of dispersing clay? Which of these four? Right? And so you're intrinsically dealing with a higher viscosity system, right? Shape affects rheology, and all because it's affecting packing, right? And then we talked about agglomeration, right? So some people did experiments where they could specifically create agglomerates of different sizes with glass beads, right? And they would separate that. Laborious experiments. They heated it to different extents and selectively picked out agglomerates of different sizes and then put it into liquids. And they found that as agglomerate size increased for any given solids loading, your viscosity went up. And then what we said was if the particles are separated from each other, the liquid is free to move. And if the particles, going back to your comment, right? Immobile liquid, if the particles are connected, and if the particles are well dispersed, you have mobile. So this is immobile liquid over here, right? There's a portion of liquid that does not participate in fluidizing. And so that's the equivalent of increasing the volume fraction. If you increase this, effectively you're having more particles, right, by having agglomerates in a given volume fraction. And so viscosity is going to go up. Right? So agglomeration affects rheology, and for your zirconia particles, what you make with them becomes a major issue if you can't separate them. Agglomeration effects. So then you can add different kinds of dispersants, and in this case, it's viscosity as a function of shear rate. If you don't have dispersants, it becomes pretty high. And then if you add some kinds of SA and SN, or stearolamine, stearic acid, and even at high shear rates, you end up having, instead of having an increase in viscosity, you actually end up having a lower viscosity. Okay. So as you add dispersants, you can change the viscosity. So we take advantage of these principles now, right, and begin to look at them in terms of either adding things to create as solid additives, and die compaction, rapid prototyping, green machining are examples where the organic additive, the small molecule or the polymer, right, remains in the solid state, and you can create shapes out of them with powders. Okay. Alternatively, different kinds of castings will allow you this rapid prototyping, injection molding, extrusion, right, solid casting. These all are cases where we look at the organic additive or the polymer in the melt phase during processing. And many things like slip casting, tape casting, drying, extrusion, all these things, right, look at using a solution to create shapes. So these are all the kinds of variations that we will look at in terms of taking information of organic additives and polymers, combining them with information about powders. We got a first glimpse of how rheological properties change when you combine the two. Now we'll take a look at how do we combine the two, and then accordingly what are the different properties of importance for mixtures that we need to control.